Same problem 12, but they ask at the end, what is the standard error of the estimate for this? Well, we've got the main answers we need, so we can erase all this so we have room. The standard error of the estimate is a standard deviation score. And if we scroll up in the chapter a little bit, let's see if I can scroll up enough so we can find the page number where we talk about this. Here. Page 171, you'll probably want to mark down so you can come back to. We talked about this last time. A regression line is connecting what is in essence the midpoint of every spot on the curve and the distribution around it. If you had an infinite number of scores, every spot, let's say this was 37, this was 38, this was 39, every spot would have a certain number of people that had that X score and would have predicted Y scores. They don't fall in a line, we know that, they're spread around it. But technically speaking, if you had an infinite number of scores, you would have a perfect normal curve around your prediction point. If you have a normal curve, that means the predicted point is the mean. And you can estimate how much the scores spread around the mean using what number? Spread around the mean is indicated by standard deviation. That's chapter 4 and chapter 5, z-scores. So what we really are asking is, what is the standard deviation with how many z-scores above or below the mean of the prediction point? But because it's a predicted value, we don't say standard deviation. Our way of saying standard deviation around the prediction point is to call it the standard error of the estimate. Okay? So the standard deviation around the prediction point is known as the standard error of the estimate. It still uses a little s as its signifier to let you know it's a standard deviation number. But next to it is a little y slash
Oh, you showed us this.
X. I showed this to you last time. See if I can get it nice and clear on here. S, and these are subscripts, y slash X, which means the standard deviation when you are predicting y from X. The formula, there's nothing new here that you haven't seen before. Sum of squares y minus, now this here is the numerator for correlation, the numerator for slope, right? It's the same thing. Sigma xy minus sigma x times sigma y over n, but this time you square that whole thing first. You divide it by sum of squares x, you subtract it from sum of squares y, you divide it all by n minus 2, and then you square root it. It's the longest, hairiest formula in the whole book.
Is there a short one?
There is a shorter one.
You already showed it to us.
Yes.
Wait, x, y,
Square root of 1 minus r squared. Isn't that the SEST equals the square root of 1 minus r squared?
And we'll get to that in a sec. But this is, if you just had the raw scores, you didn't remember that formula, because that formula is not in the book.
What's that one?
The second one I give you, the shorter one. It's not actually in the textbook, but if you've got a two-variable calculator that has already given you R and has already given you, well, really, just it's already given you R and the slope and everything else, then there's no sense having to go back and redo everything in a longer formula if there's a shorter version. Now, some people, even in this class, have not bought a two-variable calculator yet. They're still going with what's on the phone or single variable. How long will these problems take if you're having to do x by itself,
Very long.
then y by itself, then multiply all the x's by y's and sum all those up, and then do every step of these calculations by hand?
Very cool too.
Okay.
Well, at least understand it though.
Yeah, at least they would understand it real well. That's the way I had to used to do it. But it takes what could be a 3-minute problem and makes it a 45-minute problem minimum. I want you to know what you're doing. Because it's a standard deviation, it will give you the same information standard deviations did before. And so when we come down here, the application of this is, this is back on the first page we were on, said we could ask the question, what percent of scores, if I'm going to predict a score, or we said on that last one, a score of 71, will every single person with an anxiety score of 38 get a 71? No. They'll be spread above and below. How much above and below? I now know the standard deviation. I can tell you that approximately 68.34% of the scores, and here they use just average 68, 68.34% of the scores will be between -1 standard deviation and +1 standard deviation. All you'd have to do is go to your z-score table and do the same thing. What percent of scores between -1 and +1? 68%. What percent of scores between -2 and +2? 98%. Between -3 and +3, 99.9%. You can do it in a similar way. You're going to see numbers like this, confidence intervals, an awful lot in the next 4 or 5 weeks with an election coming up. Our polls show this percent of people support this candidate. Error rate ±4. What they're saying is, this is our prediction point, but we know that our true number is probably somewhere within this range. I can be 90% sure it's between 1.64 standard deviations below and 1.64. Most of them will say 90% or 95% confidence. Well, that's what we're going to start doing in chapter 12 and 13. We're going to come back and do confidence like that. We're going to use z-scores in that way. For this chapter, we're just introducing the idea, and we're only going to ask the most simple question, which is, if I say that given a score of 38, I would predict you would have an exam score of 71. But if I took every possible person in the population with a score of 38, %68 of the people should fall between what actual scores? To know that, that's, I can tell you now, and it's the example they give in the book, and it's the only thing that would end up being on the exam. I wouldn't ask more than that. That's +1 standard deviation and -1 standard deviation. Now, how would we figure that out? Well, we have to figure out the standard error of the estimate first. So we said the standard error for predicting y from x equals the long hairy formula, that's the long hairy formula, but pretty much all our numbers are here. The only thing we don't have is sum of squares y, but we would just come in here. I've still got everything on my calculator. I haven't turned it off. So I would just go over to the sigma y, square it, times 10, and I would say 1806.4.
Where's the times 10 coming in from?
The what?
You said times 10?
If I'm doing it my shortcut way, which is I look up sigma y, I have to square it and multiply it by n to get the sum of squares.
Oh, yeah, that's right, that's right.
Is it 200?
And n in this
N is
problem
10.
was 10.
Okay. That's what I thought. Alright.
And so I just took that and did it. But now I'd have every number. So I could just say 1806.4 minus 26819 minus 394 times 696 over 10 squared. Divide this section, so maybe I should write this bigger. This is divided by sum squares x 422.4. Divide all of this by 8 and square root it, and I will get my answer. Wow. And it'd probably be around, just looking at the spread of scores,
200.
with the different standard deviations,
Oh.
probably end up being around 10, maybe 11, somewhere in there. It's not a huge number.
So we would put S y over x equals, and like,
The standard of the estimate equals.
right,
Now, if you had earlier solved either the slope numerator or the numerator for the correlation coefficient, you'd already have this number, right? That's why I always solve that and I always write it down, because by the time I get to this, I don't want to have to do it again. So if you're going to do it the raw score way, we can see how long it would take to do. You can sort of time me here. So,
5 minutes already.
10.86, 10.87 rounded.
About 51 seconds.
let's say 50 seconds.
10.87.
Yeah, about 51 seconds.
So it looks hairy, but you can do it in less than a minute if you have all the numbers to
Oh,
drop
you
in.
got, oh man.
Oh, man.
What'd you get it for? Oh, we had already solved that. Oh, cause I forgot to subtract it by SY.
It's a lot of steps, isn't it? Which is why.
Oh wait, no, because I did the smaller one, but I had SSY wrong completely.
That can make a difference.
Because I just went in and I didn't I went in on the calculator and tried to do it and I did it wrong.
Let's pull up and show you the other equation just as a reminder.
Is there a specific, like, you can only use the smaller equation if kind of thing?
Nope.
Or can you use it the whole
You can use it the whole time.
time? So when you mean by you can only use that, it's not a two variable stats calculator, so.
Well, the two variable stats calculator is going to give you R immediately, right?
Right.
So if you don't have R, if you're going to have to solve R the long way, then you're going to have solved each other portion of this you're gonna have all the numbers, it's just as quick to drop them in. If your calculator gives you R to begin with, this is all of a sudden a pretty easy formula. This formula says 1 minus R squared, the square root of 1 minus R squared times sum of squares y over n minus 2 square rooted. So now, the only one we would have had to find out is sum of squares y. We did that in a couple seconds. We showed you how to do that. So now it's 1 minus negative 0.69 squared. Multiply that by sum of squares y, we said is 1806.4. Divide by 8.
That's the one I did.
Square rooted.
But I tried to.
Why do you have parentheses in the parentheses?
To remind you that this is a negative. But of course, once we square it, that'll disappear.
I tried to square sy to get SSY, but obviously that's way wrong.
That is way wrong.
Yeah.
That's way wrong.
So this ends up becoming 0.5239. Multiply that by 1806.4 equals, divided by 8 equals, and then we just square root the answer. .87. Exactly the same. Once you have 10.87, you can answer the question, if you had an anxiety score of 38 and we predicted a Y score of 71 point something or other, and I said, okay, you predict 71, but
71.60.
71.60? And I said, well, okay, not all of them will fall there exactly. About 68% of the scores would fall between what values? It would be 71.6 plus or minus the standard error of the estimate. So 71.6 plus 10.87, 71.6 minus 10.87. Because it would look like this. Again, we pull it off the prediction line. This is page, what page did we say it was?
171.
Yeah, 171. This is exactly what the chapter is saying. These are the diagrams. It says if I predict 71.60, then I know that 68.34, or 68.26 will be the exact. Percentage of scores would fall between one standard error above and one standard error below. So somewhere between 82.47 and 60.79.
So that stuff on the right, is that an answer to a specific question?
That'll be an answer to a specific question. That's the full answer to problem F on number 12. And it's the most complicated thing I might ask on the exam. It's one thing to find the standard error, it's another to remember what it means.
Okay, how do you find R squared? Because it's.
You take R and you square it.
Okay, yeah, I get that, but I squared. Oh, I forgot to subtract below one.
That's where the errors come. You can put all the numbers in the right place, and you've seen me do it too. You can make just tiny little mistakes, but they're extremely important mistakes, aren't they? So, and it seems like the littlest thing, forgetting to subtract it from 1. See, almost everything else you can save yourself by just seeing what's on the calculator. This is one area where having the $120 calculator can come in handy, because if you know where to look, it has the standard error of the estimate. The little one doesn't. The little one gives you everything else you need. Standard error is used so seldom that to solve one by hand without any safety net, you can survive. But it gives you R, it gives you the slope, it gives you the intercept, it shows you how to do the predicted value, it does everything you can use except this calculation here. This is the only one we're using that your calculator can't do for you. You've got to do it by hand.
I'm still probably gonna do it by hand, I'm not even gonna try and look for the error.
Yeah, do it. I mean, if I can do it in 51 seconds with all the information there. You just have to go systematically. And the way to do it systematically on the big one, do this first. Start here. Then you multiply this by -1 to make sure it's negative and just add it to this number. You square that number, divide by this. Multiply that by -1, add it to this. Take the whole thing, divide by 8, write that down, and then go in and do square root. Okay. I will assign problems for Tuesday.